guys, welcome to another calculus video. Today we're going to be talking about my personal favorite topic, related rates. Now related rates are super important because they are a real life application. Yay!
Hooray!
Which usually I don't like, but in the case of calculus they're actually super fun to do. They are very difficult to gain a grasp on, but once you figure it out, it's actually pretty simple. So we're going to jump right into it. There's some skills we need to review first, so this is going to be a long video, but I hope you'll stick through with us. So first we're going to review implicit differentiation. So here our question says to differentiate with respect to t. Now what this means is that we're going to assume that y, in this case, is going to be y of t, x is going to be x of t, and z is going to be z of t. And so this means that all of these are functions of time. So over time these are going to change, but this equation is always going to be satisfied. So first we just need to differentiate, assuming that these are all functions of t. So the derivative of y squared is going to be 2y dy over dt, and of negative xz is going to be negative x dz over dt minus z dx over dt equals 2 dx over dt. Now our question says to solve for dx over dt. So what we first need to do is we just need to isolate it and then simplify. So I'm going to have dy du dt minus dz over dt equals z plus 2 times dx over dt. So we're going to say dx over dt is going to equal 2y dy over dt minus x dz over dt over z plus 2. And so that's our answer. Now obviously we have in this expression 1, 2, 3 variables and 2 derivatives. So that's obviously not ideal, but in a real life situation we will have access to a lot of data. So in this case, solving for dx over dt, it's perfectly okay to have all these other expressions within it. And you'll see how this is going to be really helpful as we move forward. Differentiating in units. So this is another important topic to grasp. And so first what I'm going to have you do is assume we have some function of t, s of t. Now s of t gives, obviously it only outputs one number, so it gives you the position of an ant that's moving on a log here. So here's our log, and our ant can move left or right, but it's going to have some position. This is 0, and so this position we're going to say is going to be in meters. Now when I differentiate s prime of t, we're now talking about the rate of change of this last function. So the rate of change of the position is more commonly known as the speed or the velocity, which the units of this is meters per second. Now if I differentiate one more time, we take s double prime of t. Now it's going to be how does the velocity change with respect to time, and that's acceleration, which some of you may know is represented by meters over second squared. Now as you notice here, every time we differentiate, we end up with another second on the bottom. So differentiating something will cause your units to have another second on the bottom. Okay, now this is going to be super helpful because when we're doing related rates, typically since we have rates, that's going to be the rate of change of something, we're going to have to relate the rates of different things, and so we're going to need to know when to use meters over second, when to use meters, and how to plug these into derivatives and second derivatives and whatnot. Okay. So what really is a related rate? Well, a related rate is when we have some situation, like say, two cars that are moving on the highway, and one's moving this way and one's moving that way. We want to find the distance between them, but we don't have the rate of change of the distance between them. Instead, we only have the rate of change of this car and the rate of change of this car. Well, we can use calculus, some equations, and what's called a related rate equation, in order to actually figure out how this distance changes over time. So let's go ahead and let's start to figure that out. Now, obviously, I haven't explained much, and the best way to explain this kind of topic is to just start doing problems, because it's not really that intuitive, but once you do grasp it, you will find that all the problems are pretty easy and simple, and you just have to work through them step by step. So our first step is always going to be to draw a picture. This is super important, because without drawing a picture, how are we supposed to understand the relationships between different variables? Our second step is going to be to write an equation. And this is typically just based on our drawn picture, and we're just going to say, okay, well, based on this picture, what conclusions can we draw between, say, like we'll have variables like a, b, and c. How can we figure out how a changes with respect to c or with respect to b? And we just have to figure out all of that from the equation. So our next step is going to be to differentiate. Pretty simple. Then our final step is going to be to plug in our knowns, which that's not really a mathematical word, but it's the stuff that our problem is giving us. And our last step is to solve for unknown. And I know this may seem a little bit odd or really might not make sense yet, but I'll show you what I mean in a second. Okay, so here's our first example. I'd suggest not trying this by yourself if you've never seen related rates before, and wait for me to do it first, and on the rest of the problems you can try it by yourself. Okay, we have a square's side length increases at a constant rate of 2 meters per second. So immediately I know that I'm going to have in my equation some variable s of t. This is our side length, and our constant rate of change is 2 meters per second, which means that s prime of t equals 2 meters per second all the time. This is always true. Okay, when the side length is 4 meters, at what rate is the area increasing? Okay, so we're given the side length, which means we're going to be given s of t and s prime of t, right? And we're looking for the rate at which the area is increasing. Well, we know that our area can be represented by a of t, right? We need to find a relationship between a of t and s of t. What is that relationship? Well, as you can imagine, since we have a square, a of t is going to be equal to s squared of t. So a equals s squared. Okay, pretty simple. Now our second step is to differentiate. So dA over dt equals 2s ds over dt. And as I said before, we already have these values, so let's just plug it in. So 2, our side length, which is s, is going to be 4 meters as we're given here. And our constant rate of change is going to be 2 meters per second. And so, as you can imagine, our answer is going to be 16. All right, next problem. Now we have two ships travel alongside one another. The first is moving 2 meters per second north, and the second is moving 3 meters per second north. Now, right away, I know I'm going to have to talk about these ships, so I'm going to say our first ship is going to be ship A, and our second ship is going to be ship B. When the first ship is 300 meters north and 400 meters east of the second, at what rate does the distance between them decrease? Okay, so I know that another variable that I'm going to need is the distance, because we're looking for the rate at which the distance between them decreases. So this is going to be, actually I'm not going to call it d because I don't want to have to deal with dt over dt. I'm going to call this c. So now let's draw our picture. So we have ship B, now 300 meters north and 400 meters east, and here we have ship A. Now what's the distance between A and B? Well, we can solve this pretty easily. We know that this is a right angle, so this distance is going to be the square root of 300 squared plus 400 squared. If you know your Pythagorean triples, you know that that's going to be 500. Okay, now let's write our equation. Now we're solving for C, which is going to be this third side. So we have to write an equation for C in terms of A and B. Now, in this case, I'm actually going to change A and B. I'm going to say that A is the distance this way, and B is the position this way, right? So A minus B is going to be this leg. So this leg is going to be A minus B. So we can say that C is going to be equal to, as we said before, we know that C squared equals A minus B squared plus 400 squared. And that's our just fundamental Pythagorean theorem. So now we could take the square root here, but I think I'm going to just differentiate from here. So we're going to have 2c dc over dt equals 2a minus b dA over dt minus b over dt. And this is just the derivative of 400 squared is just 0. So now let's plug in all of our numbers. We know that a minus b is 300, as we said before. we know that c, because we just solved for it, is 500. And we just have to figure out what dA over dt minus dB over dt is. So dA over dt is 2 meters per second, and dB over dt is 3 meters per second, because remember, the change in the position is just the speed. So that's what that is. Now let's plug everything in. 2, c is 500, equals 2, 300. And we said 2 minus 3 is just going to be negative 1. So if we solve for dc over dt, we're going to get dc over dt is 300 over 500 times negative 1 is just negative 3/5. But your teacher asks, negative 3/5 what? Of course, since this is the distance between something, this is going to be in meters, and we're talking about the rate of change of that, so that's going to be meters per second. So that is our answer. And as you can see, this number is negative 3/5, because over time, okay, let's look at one more problem. A helium balloon rises at a rate of 3 meters per second. So I already know I'm going to have some variable about a helium balloon's height. So I'm going to call this h. And Thomas runs towards it from the west at a rate of 3 meters per second. When Thomas is 300 meters to the west of the balloon, which is 100 meters in the air, at what rate, actually, I'm sorry, this shouldn't be 100 meters, this should be 300 meters. At what rate does the angle of elevation between Thomas and the balloon increase? Okay, let's talk about this. So the first thing we're always going to have to do is draw our picture. So we have our balloon, it's going upwards here. We have our flat ground, and we have Thomas. What a nerd. Here he goes. He's running this way. Now I said that the height of the balloon here is going to be h of t. And I'm going to say that the distance between Thomas and the balloon is going to be represented by t. And then what we're solving for here is we have the angle. So the angle from, we're going to assume Thomas's height is 0, of course, because this is a math problem. Everyone's height is always 0. This is going to be theta. So what is the relationship between h, t, and theta? Well, hopefully you know what tangent of theta is, because tangent is opposite over adjacent, which is going to be h over t. All right, let's differentiate. So secant squared theta, d theta over dt, equals, I'm just going to replace dh over dt and dt over tt as just t prime and h prime. So we're going to have h prime t minus t prime h over t squared, or d theta over dt equals h prime t minus t prime h over t squared secant squared theta. Okay, so now we just got to plug everything in. H prime. Well, we're already told that the helium balloon is rising at a rate of 3 meters per second. Well, we know that the distance is 300 meters to the west, so that's 300. T prime. Well, we know Thomas is moving 3 meters per second to the right, so that should be 3, right? No, that's wrong, because Thomas moves east, the distance between him and the balloon is decreasing, so this is going to be negative 3. And of course, this distance here at the top, this is going to be 300. Now, t squared, we already said t was 300. And secant squared of theta. Well, so in this case, theta is going to be the arctangent of h over t, which we know that h and t are the same, so it's just arctangent of 1, or theta equals pi over 4. So secant squared of pi over 4, well, cosine of pi over 4 is square root of 2 over 2, which means secant of pi over 4 is just square root of 2, and secant squared of theta is just going to be 2. Okay, well, I'm just going to go ahead and cancel one of these 300s with that. And also, since there's 2 of these terms, I'm just going to cancel the second term with the 2. And we're just going to end up with 3 over 300, which is 1 over 100. So at this moment, when Thomas is this far and the balloon is this far in the air, our angle between the ground at Thomas and the balloon is going to be increasing at 1/100th of a radian, because remember, theta is always going to be in radians per second. Perfect. And that's our answer. Now, I know this was a long video and we covered a lot of stuff, but I think I will release another video about related rates because they're just so important and they're also very difficult to grasp. So I'm going to try put a few more examples, but I hope you found this helpful, and I'll see you in the next video.